Okay, so it's great to introduce Marco Mazzucchelli from Lyon. He's also an old friend of the workshop. And he will talk about closed geodesics and the first homology group.
Thanks a lot, Leonardo. Thanks for inviting me since 2009. I never missed, I think this has been the most important cycle of conferences for me. Many of my collaborations started at this cycle of conferences. So I enjoyed very much. I hope we will have 20 more years or 40 or I don't know. Right. So today I'll talk about closed geodesics and its joint work with Gonzalo Contreras. I'm sure many of you know it. Unfortunately, recently passed away. So this is also an occasion to talk about his work, and this is our last.
Gonzalo was in the first meeting.
Gonzalo attended the very first, right. And I met him here in 2009, so I thought it was a good occasion to talk about this work. Okay, so let me start with the motivation for the main theorem that I will give in a moment, in a little bit actually. So motivation. Much space actually. So let me denote by curly GK the space of, say, some manifold M, the space of Riemannian metrics on M, and I put the K here to specify that as a space, these are all smooth metrics, but as a space, I endow it with the CK topology. Perhaps I write it here. Right, and so the motivation for the theorem that I will present is this really amazing theorem of Gonzalo from 2010. 2010, published on the Annals. The theorem is the following. So it says you have a closed Riemannian manifold. And it goes without saying, but in this talk, all closed Riemannian manifolds have dimension at least 2. Geodesic flows in dimension less than 2 is nothing to say. So I will write it just once, dimension at least 2. And there's actually an extra assumption, which I will discuss in a moment. And so the theorem says that there exist a open and dense subsets of G2, so Riemannian metrics, which is open and dense in the C2 topology. Such that for every metric in this open and dense subset, there exists a non-trivial hyperbolic basic set. Sometimes in the literature, people just say basic set. It goes without saying it's non-trivial and hyperbolic. Let me tell you what it is. It's a classical object from dynamics, and where at IMPA, many people are experts in dynamics, but nevertheless, I should say, for the geodesic flow of G. For the geodesic flow of the Riemannian metric G. So non-trivial hyperbolic basic set is an interesting, dynamically interesting invariant set. So I give you the definition. Perhaps I put a star, and I give you the definition up here. So let me denote by phi t the geodesic flow on the unit tangent bundle of my manifold with respect to the Riemannian metric that I consider. Geodesic flow. So its orbits are just the speed curves of geodesics. And now a non-trivial hyperbolic basic set is an invariant set, lambda. So lambda is equal to phi t of lambda for every t. It's compact, non-empty. And it satisfies these three properties. So such that property 1, it's locally maximal. I don't think local maximality has been really mentioned, although it was it had to do with the results of Victor and Bajac, presented by Victor and Bajac, but I don't think it's been explicitly mentioned. So it's locally maximal, meaning that it's the largest invariant set in some neighborhood of it. So I write it like this. So lambda is inv, where inv means larger invariant set or whatever I write inside, and then I just take some neighborhood unspecified of lambda. Okay? For instance, a hyperbolic periodic orbits is a locally maximal invariant set. Indeed, the second condition is hyperbolicity. So it's hyperbolic, meaning that if we take our phase space, the unit tangent bundle, and its tangent bundle over the invariant set splits, you have a continuous splitting as a stable subbundle plus an unstable subbundle. And so this is not a smooth splitting, but it's at least continuous. And it's invariant and preserved by the differential of the geodesic flow. And the geodesic...
You also need the vector field direction.
Oh, thanks. Right. I always forget that. She's actually a source of headaches when one writes hyperbolic dynamics for flows. This plus the x, so the line bundle generated by the geodesic vector field, or Reb vector field on the unit tangent bundle, geodesic vector field. So this splitting is preserved by the differential of the geodesic flow. The geodesic flow, of course, preserves the vector field entirely and exponentially shrinks stable and unstable vectors in positive and negative time, respectively. Perhaps I don't write it. I'm sure most people here are familiar with hyperbolicity. Okay, so dot, dot, dot for the hyperbolic conditions. And then, so this would define a basic set, but possibly trivial. And a trivial basic set would be a periodic orbit. So non-trivial means it's not a periodic orbit. It's not a hyperbolic periodic orbit. No, actually, I forgot one extra condition. So third condition is transitivity. So there exists a dense orbit in lambda. And lambda is not just a periodic orbit. And of course, you can define this notion also for diffeomorphisms. It's so you don't do mistakes like the one I made. What you have to think, the way I think about basic sets is, so a typical example you should keep in mind is, let's say I do it for diffuse, would be the basic sets generated by transverse homoclinics of a fixed point, of a hyperbolic fixed points. So if you have a hyperbolic fixed point of a diffuse, and for flows, this would be the picture on a transverse section. If it's hyperbolic, it has a stable and unstable manifold. And, right, so let's say that this is stable, and this is unstable. And a homoclinic, it's been introduced by Vincent in his talk. For diffuse, it would be a point of intersection between stable and unstable manifolds. And once you have if the homoclinic is transverse, so this is a point that in the future, if you apply the diffuse, it stays on the stable manifold, so it gets closer and closer to x, and asymptotic. It's asymptotic to x in positive time, and in negative time as well. So this behavior tells you that actually this intersection generates lots of more intersections, and there's a very interesting picture that comes up. And it turns out that if you take a neighborhood of x, And this neighborhood contains a basic set for some iterate of the diffeomorphism, some very large iterate of the diffeo. If you don't want to take iterates, you will have a basic sets in a neighborhood of the homoclinic trajectory. So this is what one can have in mind. But the idea is that basic sets are dynamically messy, but where messy is intended in a positive way, where the dynamics is interesting. Right, I didn't draw it, but because it's kind of you should imagine it as a singular set, but it's an invariant set that is somehow contained in a neighborhood of the fixed point for some iterates of the diffeomorphism. If you don't want to take iterates, it will be distributed, it will be around the homoclinic trajectory, the orbit of your homoclinic point, the homoclinic orbit. Okay? Right. It's a kind of a Cantor set.
Did you ask that lambda is connected or not?
No, compact. No. Right. So, in particular, this theorem. Perhaps let me write down here. As a corollary, this theorem implies that for every Riemannian metric in this family, the topological entropy is positive. I write h top of G, meaning we've already heard about topological entropy in this workshop. So this is the topological entropy of the geodesic flow of G. So it's positive. And there's also exponential growth of periodic orbits. I didn't forget that there's an assumption missing. I'll come back to that. Perhaps let me just mention that this theorem is relevant it's relevant in every dimension starting from dimension 2, but in dimension 2, meaning the dimension 2 of the Riemannian manifold, more is known. Perhaps I quickly write it. So remark, because it has little to do with this talk, but in dimension 2, there are stronger results. Knieper and Weiss in 2002 proved the same result, building on earlier result of Contreras and Pater 9, who was essentially the same result but only for surfaces, extended this result in the C infinity topology. So true for, say, U in G infinity. So same statement, but replace G2 with G infinity. Well, I mean, the openness, you can leave it in the C2 topology, but the denseness is now in C infinity denseness. And the density. Right, and another result, still in the C2 topology of Gonzalo and myself, from about 2021, shows something more, but in the C2 topology, shows that there exists U in G2, open and dense, such that U is contained in the union of, say, A, the joint union of A and E, where A is the space of NS of metrics. And E is the space of metrics with a generic elliptic closed geodesic. Perhaps I don't explain what generic means, but it's generic in the sense of Birkhoff normal forms. And for an NS of metric, you have a basic set. The whole phase space is a basic set. And if you have a generically elliptic metric, you must have seen this nice picture of Arnold that shows the complicated dynamics around the elliptic fixed points of a diffuse. So around the elliptic generic periodic orbit, closed geodesic in this case. There's a mass, and this mass contains horseshoes and basic sets, hyperbolic periodic orbits, all sorts of things. Right, so this is stronger than that. It also implies what's called the stability conjecture as a corollary, kind of a almost direct corollary of this statement that says that a C2 structurally stable Riemannian metric on a surface must be anosov. It was our motivation to study this. But perhaps I don't write it because it's not the topic of today's talk. Now the topic of today's talk is the missing assumption. Why do I have, sorry, I didn't hear you well, Alberto. So why do I have what?
This set U, isn't the statement just A union E is dense?
Ah, yeah, sure, it's just the way yeah, sorry. So the statement is,
A union E is dense.
sure, I stated this, yes, thank you. Yeah, if you want, I can take U equal to, sure. It's just that I was in the mindset of Gonzalo's theorem, so just my way of writing. Yes?
In the region of Canteras, it's essential that it's done for metrics.
Oh, yes, thank you. Right. For Finsler, Newhouse, so for Hamiltonian systems, so studying this, these are all perturbation theorems, right? Because we cannot, for a given metric that don't say anything. Working with Finsler metric is the same as working with general Hamiltonian systems, and there are older techniques for that. But thanks for asking, because this is really the crux of the matter. We're working with Riemannian geodesic flows and not with Finsler geodesic flows. So this theorem, for instance, and the stability conjecture were known in the Finsler case, and this is Newhouse. It's not highly non-trivial, but any dimension, absolutely, yes, right, thanks, indeed. Right, now, back to Gonzalo's theorem, because there's a missing assumption. They came out in a conversation with Egor Shelukin. Actually, Egor noticed it. So the missing assumption is it's pretty much a typo, but let's say it's assumption, star, I don't need it anymore, but I want to keep the statement. So assumption star. So the extra assumption is that we need a Riemannian manifold such that there exists a residual subset, so countable intersection of open dense subsets of Riemannian metrics in, say, in G2 of M, such that for every G in V, there exist infinitely many closed geodesics for the metric G. And Gonzalo was citing a famous result of Rademacher that claimed that it took this for granted. It took this as a true statement for every closed manifold, citing a famous result of Rademacher. But this famous result of Rademacher, as Egor noticed, only holds for simply connected Riemannian manifolds. So let me mention a few things about this extra assumption that is needed, crucially needed for Gonzalo's theorem. So this extra assumption is verified, so it's true for, it's true for simply connected M. So when pi1 of M is 0, is 1. And this is Rademacher, Hans-Becht Rademacher. And many of you know that there's a famous conjecture in the field that says that every closed Riemannian manifold dimension at least 2 always has infinitely many closed geodesics, unconditionally. It's a conjecture that for certain manifolds is similar to the Colli conjecture. For other manifolds is similar to other growth estimates for periodic orbits results. Let me mention just here that, so it's, as of 2025, it's known that many closed Riemannian manifold M has infinitely many closed geodesics unconditionally. Infinitely many closed geodesics for any choice of the Riemannian metric. And examples?
Here, the first equation of the space is conference of this, because the equation of Leibniz, the same situation of equations of Rubin.
Sorry, I'm missing your question. Can you say it again?
Okay, the first equation of the planes ferry spectrum is the same equation of the Rubin. No?
The first equation?
No? The equation of the Rubin.
Maybe you can. Maybe,
Equation, of course, of the case of sensitive frequency is first sense of the Fourier. Okay.
maybe we can discuss it at the end of the talk.
Same equation is the Hilbert. We have the Lagrangian lines of plane ferry spectrum. Case of the sensitive flow.
I'm sorry, but maybe you can talk later.
Make things of
I look for, I promise I look for you at the end of my talk. I won't forgive you. I won't forget you, not forgive you. Sorry, it was completely involuntary. Okay? Right. So, yeah, so many closed manifolds have infinitely many closed geodesics for any choice of the Riemannian metrics. Examples, so two famous theorems that most of you know actually, but nevertheless, it's always a good occasion to, there's always a good occasion to remind this theorem. So simply connected manifolds whose cohomology is, say, cohomology, say, with real coefficients, for instance, is not generated by single element. It's not polynomials modded out by an ideal. So this is, so if the manifold satisfies this, then there are conditionally infinitely many closed geodesics because there's lots of homology in the loop space. So this is the case that is not the Conley conjecture in terms of the multiplicity results. It's a famous theorem of, perhaps I don't write because it's many people, but it's a combination of theorem of Gromwall and Meyer together with Viguier, Poirier, and Sullivan. Also don't write because most of you are familiar with it. And another case which is perhaps much less known, some of you know, but I'm sure not all of you, is a very nice paper of Bangert and Hingston, who confirms this for non-simply connected manifolds whose pi1 is infinite abelian. Difficult case being when pi1 is z. And again, dimension at least 2, so it's not, the circle is not included, obviously. So this is Bangert and Hingston, and I will employ it later on. Right, so, but surprisingly, this assumption is not known to hold for a manifold with a general non-abelian infinite fundamental group. And the question becomes tricky and has to do with group theory a bit, which kind of fundamental groups, which property kind of fundamental group can a group actually have in terms of conjugacy classes. And so it's a bit complicated. There are some partial results, and for me it was an excuse to apply some of the techniques that I've been working on with Gonzalo in the last few years. And a corollary of our theorem would be, it's actually not so remarkable, but a corollary of our main theorem that I haven't given yet would be that, for every k from, say, from 2 to infinity, actually, well, anyway, maybe I can write it differently. So if you have a closed manifold with non-trivial first Betti number, so first homology group with, say, real coefficients or rational coefficients is non-zero, then there exists C2 open and C infinity dense, C2 open and C infinity dense set of Riemannian metrics G, such that for every G, sorry, set of Riemannian metrics curly U, such that for every G in curly U, there exist infinitely many closed geodesics, and indeed the closed geodesics of arbitrarily large length. You could also ask a little bit less than this. I could ask this condition for some finite cover, some finite covering. Covering space. So, to be fully honest, this is not such a great statement, but it was an excuse to to apply certain techniques that we know. And the main theorem we have, it's perhaps more interesting. So let's see. Right, so let me explain what's behind the statement. And right, so you may guess, and since I'm asking that the first homology group is non-trivial, I'm actually employing Aubry-Mather theory for geodesic flows, which only makes sense when for geodesic flows only is an interesting theory only when H1 is non-trivial. So let me give you a couple of definitions on Aubry-Mather theory, just enough to state the main result. So Aubry-Mather theory. So Aubry-Mather theory is a beautiful theory for Hamiltonian systems of so-called Tonelli Hamiltonian systems that include geodesic flows, but I will only give it for geodesic flows. That has to do with action minimization. Studies orbits that minimize action in a certain sense, or more generally, measures that minimize action, suitable notion of action. So let me quickly remind this. So I have my closed Riemannian manifold, Mg, dimension at least 2, and first cohomology group. So first cohomology group, which is the same as the first homology group, is non-zero with real coefficients. So this will be always the de Rham cohomology for me. Now I'm going to denote by curly M. The space of closed Borel probability measures. Closed Borel probability measures. Probability measures on the phase space of the geodesic flows. Usually geodesic flows are defined on the unit tangent bundle, but in Aubry-Mather theory it's better to work on the full tangent bundle, or considering geodesics of any speed. So on Tm. Now this is all clear except perhaps this condition, closed. Closed just means that, so closed means, perhaps write it here, closed means that you have probability measures mu such that if you integrate an exact one form seen as a function Tm, you get always 0. So integral of over Tm of df, so the differential of a function f against the measure d mu is 0, and this is true for every f. Now, example of closed probability measures. First example, perhaps the simplest one, is measures that are Dirac on closed curves. Or measure, perhaps Dirac is not the right word, measures of integration along a closed curve. This is gamma is so where gamma is, say, a closed curve in the underlying manifold M. So I denote by tau gamma its period. So it's a function, it's a curve defined on the circle of period tau in M. Smooth, let's say. And the second example, so it's clear that these are closed. Second example, which is perhaps a little bit less clear, but it's a very simple exercise, invariant measures. So mu that are invariant under the geodesic flow. So if you mu such that phi t star of mu, phi t star of mu is equal to mu, where phi t is the geodesic flow as before, but defined on the old tangent bundle. Phi t from Tm to itself is the geodesic flow. Right. So this is the notion I'm interested in. I'm going to continue on the left. So I said the Aubry-Mather theory is about action minimization, so I have to tell you what action is. Action is the analogous action that you have in symplectic geometry. Well, there are several versions of it. And precise definition is the following. So actually here you don't have a single action, but you have an action for every choice of a one cohomology class. So let me denote by sigma a cohomology class. So I don't write the coefficients R anymore, but it's always the round cohomology class. And you want it to be non-zero. So sigma different from 0. You can also take 0, but let's say non-zero. So the action is a function on the space of measures that I introduced. And so it's defined as follows. So the action of a measure mu is the integral over the tangent bundle against the measure mu. So it's kind of a linear function in the measure, so to say. And the function that you integrate should be the Tonelli Lagrangian associated to the geodesic flow and twisted by this, twisted, so to say, by this cohomology class. So it would be 1/2 v squared, where this is the norm measured with the Riemannian metric that we have. So this also depends on the Riemannian metric, but that I fixed once for all for now. Minus sigma v. So here I'm a bit sloppy with the notation. I'm taking any closed one form that represents the cohomology class. So this is the action I'm interested in. And one last definition, and then I can move on to the statement. It's the so-called Mather alpha function, which in different forms already appeared in this workshop, actually in the talk of Gabriele. So Mather alpha function, it's sometimes known as Magnier critical value, and perhaps there are even other names. So in this business, it's denoted with alpha, because Mather denoted it as alpha in his first paper. So it's a function defined on the cohomology, on the first cohomology. So alpha of sigma is minus the minimum or the space of closed measures, probability measures of the action. So there's a simple compactness theorem that guarantees that this minimum is always achieved. And actually, Ricardo Magnier proved that the minimal measures are, the minimizer are automatically invariant measures. So this is always achieved at invariant measures. Invariant measures. Like in point 2 of the example. And an invariant measure can be approximated by so-called holonomic measures. So it turns out that you can actually define the alpha function as, instead of working with measure, just working with curves. But in this case, you don't get a minimum, you only get an infimum that may not be achieved. So this is also equal to minus the infimum over all loops gamma. Now gamma is a loop in the underlying Riemannian manifold M, parametrized with any period. And then you take a sigma of, let me write just a sigma of gamma. The action of gamma is the action of the Dirac on gamma. So, and you have to be careful. This is not the usual action in symplectic geometry. It's rather the usual action divided by the period. Right. So now, this in general is not achieved. It's an infimum, whereas this is always achieved. But when it is achieved, so if this is achieved at gamma, then gamma is a periodic orbit of the Hamiltonian system dual to this function. And so if I didn't have this, the periodic orbit would be a closed geodesic, but it turns out that if you add to this term a closed one form, you're not changing the dynamics. So the curves at which the infimum is achieved are closed geodesics, but of a very special kind. And they're called sigma minimal closed geodesics. Definition, so if it's achieved, then definition, then gamma is a sigma minimal closed geodesic.
Sorry to interrupt you.
Yes.
But you wrote there as a corollary, but actually this is your main result, right?
No, I think the theorem, I prefer the theorem.
But it's a corollary of what?
Of the main theorem that I haven't stated yet.
So
Sorry about it.
you state the theorem and then it's a corollary.
Yes. No, it's just that I wanted to tell the whole story of how I got to work on this, and it came from...
Just for suspense.
Yeah.
It's for suspense, and also to say that this class feels Gonzalo's can enter into... right. So, right. So, yeah, just... oh wow. Just to have something in mind, I was on the left, so I can erase Gonzalo's theorem, I'm not using it anymore. It was just somehow the excuse to work on this. So perhaps an example to keep in mind. So first of all, sigma minima closed geodesics are also kind of length minimizing locally in a suitable sense. There are certainly, let me say something that's clearly true, there are geodesics, there are closed geodesics with no conjugate points. For those of you who are more familiar with Riemannian geometry, an example of sigma minima closed geodesic, perhaps the simplest one would be you take a torus. So this is your manifold. And so it's, let's say, embedded in R3, so it inherits the metric, and then you create a small neck, like this. So still a torus. And so here you see that you have a closed geodesic, gamma. I oriented in the way I drew. And let's call theta the angular variable on every meridian. Call it like this, theta, so it's a S1 valued function. So d theta is a closed one form, that's not exact. Then the Riemannian metric is the one corresponding to the picture. Then gamma is d theta minimal, closed geodesic for that Riemannian metric. So this is an example, a particularly simple one. Right. Right, and finally, let me state my theorem, because I'm running out of time. So it's, again, joint to work with Gonzalo, as everything I'm talking about here. So sigma minima closed geodesics, as I already said, do not always exist in general, but if they exist, So if there exists one, let's say if there exists a minimal closed geodesic, meaning when I say this, when I write this, I mean if there exists a sigma minimal closed geodesic for some sigma that is non-zero. For sigma equals 0, there are always the points. They're not closed geodesics, but they reach the minimum. Right, so if there exists one, then there exists a Riemannian metric. So I fix my Riemannian metric once for all for now, and now I perturb it. Then there exists a Riemannian metric which is C infinity close to the original one. I write it like this. Twiddle C infinity, it means C infinity close, to the original Riemannian metric, such that, let's say, let me give a name to the minimal closed geodesic, say gamma. So there exists a perturbation of my Riemannian metric, such that gamma is again a closed geodesic for the new metric, but it's also hyperbolic. So gamma is hyperbolic with a transverse homoclinic in the sense defined by Vincent in his talk, or also in the picture that I gave for the diffeomorphism, the analogous notion, for the Riemannian metric G tilde. Right, and the corollary is a pretty direct corollary of this and of a very nice argument of Magnier, who proved that when there are no minimal closed geodesics, then there are infinitely many closed geodesics of arbitrarily large length on the nose without even needing to perturb the Riemannian metric. It's a simple argument that uses Birkhoff-Ergodic theorem in a smart way. And right, yeah. So I have what 12 minutes plus epsilon left, and 15. Okay, good. So then I can try to. I won't be able to. I won't have time to give the old proof, but I want to just explain the ideas. Right. So perhaps let me leave the statement. And if there are questions on the statement, please ask. So,
in that theorem, you are fixing sigma.
in this theorem, there exists a sigma minimal closed geodesic for some sigma. For some sigma.
For some sigma.
So sigma non-zero.
So not for every sigma.
No, not for every sigma. No, that would be too much. If there's one for every, you have infinitely many closed geodesics already as an assumption. Right. Yes, yes. So that's why when H1 is 0, Aubry-Mather theory for geodesic flows is not really interesting. Right. So now proof. Sketch of the proof. Right. So let's start with sigma. Let me start with my gamma, which is sigma minimal, and sigma is non-zero. Starting point. Now, yeah, the proof combines several results from Aubry-Mather theory and from the literature on closed geodesics. So first of all, I'm going to consider the Hamiltonian on the cotangent bundle that corresponds to the problem. The Hamiltonian is the following one. So H is a function T star m. So H of P is 1/2 Riemannian norm of P. So P is a point in T star m, so it's a covector. So I can take the sum of P and any representative of sigma, which is just denoted by sigma. So P plus sigma squared. And here I have the norm on covectors, which is the norm given by my Riemannian metric, the dual. Right, so this is the Hamiltonian of the problem. And the flow of this Hamiltonian is the geodesic flow, except for a small shift. So the orbits project down to geodesics. Right, and now I'm going to employ a deep result of, an important result of Fatih and Sikonolfi from 2004. It was a So phi t in C con alphi. Actually, I think that Albert Fati spoke about it here in 2009, for those of you who were here. So I forgot the year. I didn't mark it in my notes. Sorry about it. The result says that there exists a C1 Hamilton-Jacobi subsolution for this problem. Jacobi subsolution. So let me explain. So Hamilton-Jacobi subsolution, it's a function u, C1, defined on M, real valued. So the Hamilton-Jacobi equation for this problem would be h of du identically equal to a constant, C. And a bit of Aubry-Mather theory tells you that if you have solutions of this equation, then the constant must be the alpha, the mother alpha function, alpha of sigma. Of course, I'm going very fast on these things. It's not so complicated actually, but so if you have this would be if you have a U that satisfies this, you would have a better conclusion. You would have a Hamilton-Jacobi solution. But Hamilton-Jacobi solutions in general you don't have. So a subsolution is a solution of this inequality. And of course, if I put here, when you consider the inequality, if you put here a huge constant, okay, it's easy to solve the inequality. But turns out that alpha is the minimal constant for which you may have, for which you have subsolutions. And the content of the theorem, it was a paper in Invenciones, is that this subsolution can be found regular, C1. And I think this has been even slightly improved, but I will only need C1 in my talk. Right, so now I'm going to use this as follows. So the Hamiltonian, I can use a classical duality, Legendre duality from convex analysis. It's back to already, well, forgot if you specifically said the word, but anyway, you had the dual of a Hamiltonian. Right, turns out that h of the u by convex analysis is larger than or equal to du applied to a tangent vector v minus the 1/2 v squared minus sigma v. Let me explain. Now, this term in brackets is just the dual function of this Hamiltonian in the sense of convex analysis, so Legendre dual. Right, so now this is Legendre duality, or Frenchel duality sometimes it's called. Legendre duality. And now, okay, now let me use the inequality this less than or equal this. So I define this Lagrangian function on the tangent bundle by packing together all the terms so that I obtain a non-negative function. So L of v would be 1/2 v squared. For the Riemannian metric G, I write it because I'm going to perturb it in a second, minus sigma v minus du of v plus alpha of sigma. Notice that I just packed together, I brought all the terms to the right-hand side here so that I obtain something non-negative. Let's have a look at this function. So again, associated to any function like this, you have a flow in the tangent bundle that is kind of like a Hamiltonian flow, but seen on the tangent bundle instead of the cotangent bundle. If I didn't have these terms, these three terms here, 1/2 v squared would give me the geodesic flow. If I add a constant, it doesn't affect the dynamics. And if I add a closed one form, as this is, applied to v, it also doesn't affect the dynamics. You can, exactly as it didn't affect it before. Okay, so this somehow is a Lagrangian, whose Euler-Lagrange flow gives you the geodesic flow. Right, and now And notice it's perhaps not completely obvious, but notice that, so I may perhaps say it. Notice that this Lagrangian applied to gamma dot of t, where gamma is my sigma minimal closed geodesic, is identically 0 for every t. This is not hard to see. This is since, so let's see. If we take, let's take the action of, right, so let's take the Lagrangian action of gamma. So the action sigma of gamma, this would be 1 over tau. Tau gamma is the period of gamma. 1 over tau gamma times the integral from 0 to tau gamma of the Lagrangian applied to gamma dot dt. So this is the definition of action. It's the action as I defined it. Right, the definition would be, sorry, the definition would be without this term. I should copy my notes instead of thinking. So let me restart. Sorry about it. So up. Try again. So the integral from 0 to tau gamma of L of gamma dot dt is equal to, if I divide it by tau gamma, is equal to what I defined before as A sigma applied to the direct measure distributed along gamma plus A of sigma. So it's equal to this pretty much by definition of L, keeping in mind that when you integrate du over a closed curve, the term vanishes, the Stokes. And this is 0 by definition of the Mather alpha function and of the fact that gamma is a minimal closed geodesic. And now you have the integral of a non-negative function that is 0, therefore the function is pointwise 0 everywhere. Okay, so what we have. My time is almost up, but I think I'll be able to reach a decent point to conclude. Right. So okay. So this was the starting point. Now I'm going to perturb, and so it's all experts in Riemannian geometry know how to take a closed geodesic without conjugate points and make it hyperbolic by perturbing the metric. If you have no conjugate points, it's kind of like along the closed geodesic you have zero, you have non-positive curvature. And it's easy to perturb it to make it strictly negative, and then it becomes hyperbolic. So the details are as follows. So you take a function of one variable s, which looks like this. So it's perhaps in color. Looks like this. So you have the function is, I call it f of s. This looks like white. Doesn't matter. Take a step function like this. So this is f of s. So f of s is positive outside the origin, and it's convex at the origin. And so it becomes constant after a while. I mean, I'll write all the conditions because I drew it. But last condition is f is infinity small. And now, you take this function, you pack it, you use it to create kind of a step function in your Riemannian manifold, rho of let's see, right, so you create the function rho of x, which is, let's say, f of distance from x to the closed geodesic gamma. And you arrange this to be smooth. Right? And now it turns out that gamma is a hyperbolic closed geodesic for g tilde, which is e to the rho g. It's very similar to something Alberto said this morning in his talk. You're just bumping up the Riemannian metric, the Riemannian norm, outside of your curve. Right. Now, I take 2 more minutes, and I promise I will stop then. so now, so what did we do? We had G and we perturbed it to get a C to get G tilde, which is C infinity close to G. Just bumped it up a little bit. And now we take the Lagrangian L that I defined before, and I replace it with L tilde. I say it in words. L tilde is the same as L, but I use the metric G tilde instead of G. Okay? So, so what I obtain now is that, so this L tilde is going to be larger than or equal than L. So this uses G tilde instead of G. Right? So this is larger than or equal to L. But now, since I bumped up a little bit the Riemannian metric, turns out that L tilde of V is, if L tilde of V for some vector V is 0, then V must be based at some point. The vector V must be based at some point of gamma. And you can also, it's not hard to see that L tilde of a scalar R times gamma dot of T is equal to 0 if and only if R is equal to 1. Okay? And now my time is almost up, but I'm also almost done. I just have to write one last statement, which actually would be the beginning of the proof instead of the end, but I think it makes a point, and then I can stop. So next point, I have this crucial lemma, which contains most of the difficulty of this problem. It says that there exists a G tilde geodesic zeta from, so it's an open geodesic. Zeta is different from gamma, geometrically different from gamma. So it's not a closed geodesic. And such that the total action of zeta is finite. The integral from minus infinity to infinity of the Lagrangian along zeta dot dt is finite. And now I'm done because, so this is an integral over the whole real line of a non-negative function that vanishes pretty much only along gamma dot. So the only way for this integral to be finite is that zeta must be asymptotic in the future and in the past to gamma dot. So this implies that zeta, so this immediately implies that zeta is a homoclinic to gamma. And, well, the theorem said transverse homoclinic. So if you want only a homoclinic and not necessarily transverse one, well, that doesn't bear all the dynamical consequences. But if you're happy with just one homoclinic, you can reach it with a very explicit perturbation. If you want it to be transverse, then it's well known in dynamics that given a homoclinic, even in geodesic flow dynamics, given a homoclinic to a closed geodesic, you can always make it transverse with a C infinity small perturbation. There's an argument that I learned from Burns and Weiss, and that they attribute to Petrol, I believe. You can do that with a C infinity small perturbation. Now, this lemma contains all the difficulty, and perhaps just a couple words. The proof is based on certain spectral invariance techniques from closed geodesics. And I'm going to stop here.